Hi, my name is Ruki, and I'm going to introduce you to the concept of excitons. An exciton is a fascinating concept in the world of physics, especially in the field of condensed matter physics and semiconductor materials. To understand excitons, we should start with the basics of what happens when light interacts with matter. When light shines on a material, it can transfer its energy to the electrons within that material. These electrons can then jump to higher energy levels, a bit like climbing up a ladder. This process is called absorption. So when the electrons absorb this energy from the photon, they leave behind holes in the material, which are essentially spaces where an electron used to be. Now, here's where excitons come into play. Imagine the electron that jumped to a higher energy level because of the absorbed light. It left behind a hole in its previous position. The electron and the hole are attracted to each other, like the opposite poles of a magnet. They form a bound state due to this attraction, and this bound state is what we call an exciton. Excitons behave a bit like particles themselves, even though they're technically not. They have properties similar to those of electrons and positively charged particles called holes. Excitons can move through a material, much like electrons can, and they can also interact with light. When an exciton encounters light, it can release the absorbed energy, sending the electron back to its original position and disappearing in the process. There are different types of excitons based on their behavior and how they're formed. The Frankel excitons, termed as molecular excitons, are usually limited to a single molecule within the solid material. Their energy is affected by the polarization of the surrounding medium. This type of excitons can easily move through the material by jumping from one molecule to its neighboring molecules, and they're the primary influencers of the optical characteristics of organic semiconductors due to their high binding energies. This makes them stable even at room temperature. The second type are the charge transfer excitons. They're formed when an electron and hole in the process of movement briefly occupy neighboring molecules. These molecules can either be similar or create a heterojunction with dissimilar materials, providing a pathway for the electron and hole to be bound together by the Coulomb force. The excited state of these excitons can spread across multiple nearby molecules, especially when the molecules are closely packed, as you can see in this example. Materials with significant charge transfer characteristics in the organic realm often exhibit optical properties similar to Frankel excitons. Despite primarily behaving as conventional excitonic materials, they also share key traits with chemically bonded inorganic semiconductors. The third type of excitons are the one-year-Mott excitons. This is a type of excited state found in chemically bonded inorganic materials. It's characterized by low exciton binding energy, typically ranging from about 5 to 50 millielectron volts. These excitons are unstable at room temperature due to the high dielectric constants of the materials. They have large radii spanning many lattice constants within the material. Unlike other excitons, the one-year-Mott excitons have low oscillator strengths, meaning they have a weak interaction with light. Excitons have significant implications in various fields, especially in material science and electronics. They play a crucial role in processes like light emission in LEDs and lasers. Scientists are also exploring excitons for use in technologies like solar cells, where they could help improve the efficiency of converting sunlight into electricity. Understanding excitons gives us valuable insights into the behavior of materials at the quantum level and opens doors to new discoveries and technological advancements. Thank you for your attention. I hope it was enjoyable for you. These are my references.